Hey everyone, Rajib here and welcome back to the channel. Today, we're diving into the Solid Principles, a set of 5 guidelines that will transform how you write clean, maintainable, and scalable code. Without a solid understanding of solid principles, your code base can quickly become a tangled mess, making it difficult to maintain, debug, and extend. Solid stands for single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. Let's break them down with easy-to-understand C# examples. First up, the single responsibility principle. It means that a class should only have one reason to change. Imagine we're building an e-commerce application, and we have a class called. This class handles everything related to an order, creating the order, calculating the total price, sending email notifications, and logging the order details. Now, what happens when we need to change the way we send email notifications? Or if we want to update our logging mechanism? We would have to modify the class every single time. This violates the single responsibility principle because our class is responsible for too many things. To fix this, we can break down the class into smaller, more focused classes. We can have a separate class to handle order creation and calculations, and class for sending notifications, and a class for logging. This way, each class has only one responsibility, making our code more organized and maintainable. Think of it like this. Each class should have one job, just like in a well-run kitchen. By adhering to the single responsibility principle, you make your code more modular. Each class becomes a building block that can be easily understood, modified, and reused in other parts of your application, without causing unexpected side effects. This modularity not only makes your life easier as a developer, but it also improves collaboration in a team environment. When each class has a clear responsibility, developers can work on different parts of the code base simultaneously without stepping on each other's toes. Remember, a class should have one, and only one reason to change. Next, the open-closed principle. A class should be open for extension but closed for modification. Imagine we have a class called that calculates the area of different shapes. We initially have support for calculating the area of rectangles and circles. Now let's say we need to add support for triangles. If we modify the class directly to include triangle calculations, we violate the open-closed principle. Every time we need to support a new shape, we'd have to modify the existing code, increasing the risk of introducing bugs. Instead, we can use inheritance and polymorphism to make our open for extension. We can create an abstract base class called with a virtual method called. Then, we can create concrete classes for, and each inheriting from and implementing their own method. This way, R doesn't need to know about the specific types of shapes it's dealing with. It can simply call the method on any object that implements the interface. If we need to add support for a new shape, we simply create a new class that implements the interface and provide its own area calculation logic. By using abstraction and polymorphism, we can extend the functionality of our code without altering existing code, reducing the risk of bugs, and making our applications more maintainable in the long run. The open-closed principle promotes a similar approach in software development. By designing our classes with extensibility in mind, we can easily adapt to changing requirements and add new features without compromising the stability of our code base. The Liskov Substitution Principle ensures derived classes can replace base classes without breaking functionality. If a function works with a base class, it should work with any derived class without unexpected behavior. For example, penguins and eagles are birds, but penguins can't fly. Violating LSP can lead to subtle, hard-to-debug errors. Adhering to LSP ensures derived classes are truly substitutable for their base classes. This promotes code reusability and makes applications more robust. Fourth is the interface segregation principle. Don't force classes to implement interfaces they don't need. In simpler terms, it's better to have smaller, more specific interfaces than large, monolithic ones. Imagine we have an interface called with methods like and. Now, let's say we have classes for and, while all these classes might need to, and only the class would need to. Forcing the and classes to implement the method violates the interface segregation principle. To adhere to this principle, we can break down the interface into smaller, more specific interfaces. We can have an interface with and a separate interface with the method. The class can then implement both interfaces, while the and classes only need to implement This way, we avoid forcing classes to implement methods they don't need, making our code cleaner and more maintainable. It also allows for greater flexibility in our designs, as we can easily create new classes that implement only the interfaces relevant to their functionality. The interface segregation principle encourages us to organize our interfaces like a well-organized toolbox, with smaller, specialized interfaces that cater to specific needs. This makes our code more modular, flexible, and easier to maintain. Finally, the Dependency Inversion Principle. High-level modules should depend on abstractions, not on low-level modules. In other words, we should aim to decouple our code by relying on interfaces and abstract classes, rather than concrete implementations. Let's say we have a class called that handles sending emails. Now imagine we have a class called that needs to send a welcome email when a new user signs up. If the class directly creates and uses an instance of, it becomes tightly coupled to the concrete implementation of. This tight coupling can lead to problems if we ever need to change how we send emails. For example, if we want to switch from using our own class to using a third-party email service, we would have to modify the class, even though the core functionality of creating a new user account hasn't changed. To adhere to the Dependency Inversion Principle, we can introduce an interface called with a method. Our class would then implement this interface. Instead of creating an instance of directly, the class would depend on an interface passed in through its constructor or a setter method. This way, the class doesn't care about the concrete implementation of the email sender, it only cares that it has a method. This makes our code more flexible, as we can easily swap out different implementations of without affecting the class. By depending on abstractions, interfaces or abstract classes, we decouple our code and make it more adaptable to change. This reduces the impact of changes, makes our code more reusable, and improves the overall maintainability of our applications. Let's recap the solid principles: single responsibility, open-closed, Liskov substitution, interface segregation, and dependency inversion. Together, they promote clean, modular, and maintainable code. Follow these principles, and you'll create software that's easier to extend and debug. Remember, writing clean code is not just about making it work. It's about making it maintainable, reusable, and understandable for yourself and other developers. If you found this helpful, don't forget to like, share, and subscribe for more coding tips and tutorials. See you next time.